Thank you. Thank you.
Good afternoon and welcome to Kubernetes MLSec. Francesco and I will introduce ourselves momentarily, but thanks again to all the KC organizers for putting together such a spectacular event and all the constant voluntary work that they do. Deeply appreciated. Hi, I'm Andy from Control Plane, Cloud Native Security Engineering Consultancy and Education. I'm proud to be involved with some other illustrious organizations, including the CNCF's Tag Security, where we help to assure cloud-native software as it progresses towards graduation. If you're interested in understanding how we do that, then please feel free to join us either to observe or to contribute. We meet every second Wednesday at 1 p.m. UK time. There's also a US meeting every week, which is 6 p.m. UK. And I'm CISO at Open UK, where we attempt to help steer the UK government through the murky waters of open source regulation, hopefully not passing things like the CRA in this country, and then various other bits and bobs.
Thank you very much. I'm Francesco, I'm Security Engineering Manager for Control Plane. I started my career in the European government ranks back in 2010, looking at network security, data security, system hardening. Then I moved to Inmarsat, a satellite mobile provider. I was a chief engineer for the Satellite Control Center. And after that, I joined the security operations team, where I was leading the security operations engineering team, so hands-on guys doing supporting the technology stack, enabling security operations globally for the company. And then I expanded the role, becoming head of security engineering. So my team, a larger team, would also consult the internal business units on their crazy projects. And then in 2021, I didn't want to see a network cable again in my life or a data center. So I joined Control Plane, Cloud Native Security Consultancy, as Andy will present. Thank you.
Okie dokie. So yeah, just a few words about Control Plane. This is broadly what we do. Security specialist consulting for cloud native. Zero trust and DevSecOps are woven into the fabric of our DNA. All that good stuff. Pen testing, and of course, if any of you had the opportunity to play the CTF workshop this morning, that is something that we love to do as well. We're about to open the signups for our hosted CTF. So if you're interested in that, cubesim.io, and then lots of community contributions. We love the community. Open source security is still a fairly new thing, as a lot of traditional organizations are scared of sharing that information because it might be misused. But yes, nevertheless, so that's about Control Plane. Let's talk about AI in space and all the things that could possibly go wrong. Right, we'll run through a brief introduction to the AI ecosystem, talk briefly about the levels, types of AI, because there's AI, machine learning, what really is the definition, use cases, and then focus in particular on machine learning in a typical ML SDLC or machine learning lifecycle. Based on that, we'll try and gain an understanding of the problem space securing these life cycles, which we'll see is non-trivial, especially when we're running on a Kubernetes system. We have advantages and disadvantages. Of course, everything is declarative, everything is easy to reason about, but it is still a complex ETL++ kind of problem. Then we'll get to the most interesting and technical parts, where we'll present an actual use case from the SATCOM domain and a threat modeling methodology through the machine learning security problem space, and identify risks and mitigating controls for common and some slightly less common threats affecting AI, ML, in space or in your backyard. So we'll start with an introduction to the various types of AI. The current and most basic level is what experts call artificial narrow intelligence, or weak AI. It is developed and designed to carry out a finite number of tasks, such as reactively answering humans' questions, and can only operate on a predetermined set of data. Google Assistant, Siri, Alexa, and of course ChatGPT, student's best friend, referred to some as a parlor trick. It is not it is not Skynet, it is not artificial. So the next intermediate level of AI is the artificial general intelligence, or strong AI, which is an aspiration for the next days, weeks, decades, centuries, purely theoretical at this stage. AI practitioners wonder if we've already hit a plateau with GPT 3.5. There is no noticeable innovation that's occurred since that's been released. Examples are HAL 9000 or data in Star Trek, Skynet, and Terminator. But the major differences are this is supposedly a human-like AI, and more importantly, can adapt to new rather than predetermined data sets, environmental stimuli, and triggers. Then we get to the truly hypothetical, academical, dreamy stuff, which some call artificial superintelligence, which possesses superhuman capabilities and is characterized by continuous learning and self-improvement. Examples are Ultron from the Marvel Universe or Giscard from the Asimov novels, as aptly demonstrated. Okay, so AI, fairly large domain, a large number of branches, and we thought it important to provide at least some direction to the overview of where ML actually lands. We have the machine learning, artificial intelligence ecosystem here. The use case in this talk will focus on this specific branch of AI. Machine learning is a branch of AI that focuses on mathematical formulae and statistical models that computer systems employ to carry out operations without being explicitly programmed. Instead, they can utilize machine learning to take what they have in the present context and generalize it to new tasks that modify their programs automatically. Within that ML branch, we have 3 different types, and here you can see a typical technique and use case for each. In general, unsupervised learning analyzes data without predefined labels, identifying inherent patterns, clusters, or structures within the data, and is used for tasks like dimensionality reduction and clustering. Reinforcement learning, which is what we're seeing in a lot of our chat bots these days, involves an agent that learns by interacting with an environment, receiving rewards or punishments for actions related to stimuli and behaviors that it takes with either full, partial, or zero knowledge of its environment. And the agent's objective is to maximize cumulative rewards, making it suitable for tasks where trial and error is essential, such as game playing, robotic control, taking over the world. And supervised learning utilizes label data to train a model to make predictions or classifications based on input features. The model learns to map inputs to outputs and is useful for regression and classification and that kind of thing. So supervised learning trains the model to recognize the relationship between input and associated output labels, entails giving a model a data set that's been labeled. This is relevant because we'll go through all of these stages with an AI lifecycle momentarily. And we're looking for the model to be able to generalize from the provided examples to generate some precise outputs and predicting output labels for brand new untried data. This is supervised learning. And other pieces of note here, classification is predicting a discrete or categorical output label, e.g., here's an image, is it a dog, cat, bird, etc. And regression, and a lot of AI could potentially be explained as linear regression anyway. The objective is to forecast a continuous or numerical output value, for example, predicting the price of a property based on parameters like size, number of rooms, and location, given previous data on housing in general. Okay. Hand over to my esteemed colleague, Francesco.
Thank you very much. Before I resume, I'd like to know how the transcribing work with my thick Italian accent. Does it work okay? Good enough? Super. Right, so to properly understand the intricacies of securing AI-based systems, we have to start from the AI MLOps lifecycle, which is the lifecycle that starts from data, goes through a trained model, all the way to applications that downstream customers can consume within or outside the organization. So let's talk about this lifecycle. Right, to start from the basics, I'll introduce a groundbreaking concept that none of you have heard about. DevOps, right? So good old DevOps. This is where it all started when designing AI-based systems. So effectively, I know you all very well know what DevOps is about. For those of you who don't, DevOps is a paradigm, was introduced a time ago. It's a continuous loop to join development and operations to streamline software delivery. Then when they start designing machine learning training models, they said, what are we going to do? Invent something new from scratch? Of course not. Some genius came up with an equivalent paradigm called the data ML loop, which again consists in getting data from somewhere, cleaning up that data, training models up on that data in supervised learning, and then reiterate this continuously to keep improving the model. Nice analogy, right? Well, why stopping here? Another genius, same genius, came up with something quite useful to cover the end-to-end life cycle of AI-based application from data to downstream applications, and that's called the eternal knot. The eternal knot is actually the convergence between the two loops into something quite advanced that starts from data to go then to train models, to go then to application built around those models, served as applications as part of the IT operations. But yeah, what's the issue? But the issue is, it, first of all, looks quite complex. And second is that we did a very good job in the past decade or so trying to secure DevOps by introducing security, famous shift left, in all these steps. What we need to do? We need to do exactly the same with the other loop. And by doing so, we harden, again, the end-to-end life cycle of AI-based applications, all the way from data ingestion, all the way down to downstream applications. But as we will see, this is quite a challenge. Good, sir?
Thank you very much. OK. Let's have a look at the problem space in which we find ourselves. As usual, with new, shiny, cool stuff, we have more complexity, more layers that we need to assess and secure by design and by default. We have the good old infrastructure layer that we know and love. But then we need to move to the orchestration layer, which sits on top and has a slightly different form of orchestration because of the type of workloads that we're using. That's where we define and execute the operations on the ML model itself. It's equally important, of course, to secure the data layer and the associated operations, because data, as with many other organizations, is really critical. The lifeblood of many organizations is the PII they hold, the financial information, the records. For most web applications, for AI, ML workloads, of course, it is intrinsic. It is the thing. It's how you get a model. It's how you actually infer, and it's what the value is for most organizations in that space. And finally, any app leveraging our model is an entry point to an exposure of the model and attacks such as model inversion, where potentially, as we've seen when people try and trick models into going against their programming, if you like, ultimately putting your proprietary data in a model and then in public risks things like model inversion or prompt re-engineering, pulling those things out and identifying the original source data, which is probably IP, trade secret of some importance to your organization. We're not going to go through this since we'll do it later, but this is to give a high-level understanding of how complex the end-to-end process is from data to end-user applications. So overall, the main challenges when securing MLOps have to do with complexity, dependencies, and data flows. It's a multidimensional problem that encompasses, amongst many other things, data security, model security, access control, supply chain, which now takes on a whole different context because we're talking about the supply chain of data. Arguably, configuration should be part of any software supply chain. The data here is essentially the configuration of the model. And so, enough of the theory.
Right. As usual, at Control Plane, we do one thing. We threat model everything, right? So, to navigate through that problem space, which, as Andy said, can be quite large, we use threat modeling. And how? Well, again, enough of the theory. Let's jump into a concrete use case. So, hypothetical company X. Company X maneuvers and operates a fleet of spacecrafts. Spacecrafts, they send down a constant stream of telemetry. This telemetry is quite complex, 1,000 parameters every second. Telemetry lands on Earth, special points, and then converge into centralized processing locations on the globe. Why they do that? Well, they do it for building fancy dashboards in large control centers to do one thing: monitoring and anomaly detection of spacecrafts. The most basic way to do so is to build a very large and complex decision trees based on concatenation of if, then, else, and, or conditions. It's a very reactive approach and is very ad hoc, because for every anomaly, it may change, right? So company X said, wow, we really want to do something more sophisticated. What can we do? Well, you have petabytes of data. Can you do a better use of that data? Of course you can. The company X put together a stack of technologies to move from a reactive approach to anomalies to a more predictive approach to anomalies. Can we, based on what happened, if we properly curate this data, can we figure out what can happen and when in the future? The answer is ish. So the stack was built on an infrastructure, doesn't matter, using, of course, a proper operating system. On top of it, there was a workload orchestration platform at KCD that happens to be Kubernetes, right? And then on top of it, there was a framework called Kubeflow installed, and TensorFlow, which is, again, part of the same ecosystem from Google. Those are excellent frameworks embracing a Kubernetes native way of orchestrating pipelines using containerization, in a nutshell. And then they built on top of it front-end apps, again, for anomaly prediction. Right, so company X is very security cautious. Why is that? Because they have sensitive customers. Sensitive customers require a high level of security on anything that company X manages. So yes, they did run a threat model. The threat model of this platform was based on two main assumptions. We are now dealing with a sophisticated threat actor with significant capabilities, and the machine learning platform is used to inform only, is not used for command and control, so to operate directly spacecrafts. And out of scope was the over-the-air communication, the ground segment backbone, aka those orange lines from the remote sites to the central processing data centers, and the data centers and the infrastructure itself. Super. Now, brace for impact. This is the reference architecture, aka and data flow diagram at level 0 of the how the stack looked like. Again, we descope for now the infrastructure and the underlying Kubernetes deployment. We only focus on the MLOps, aka Kubeflow and TensorFlow stack, and whatever they build on top, right? Let's spend a minute on this diagram. We have 5 audiences. Infra admins, descoped. Cluster admins, somewhat descoped. Machine learning and data engineers, they define the pipelines and then define the jobs to train the models. They are in scope. Data scientists and SMEs, they do all sorts of stuff on the individual tasks, and they are in scope. And then also in scope are the systems consuming through a front-end application the trained models, aka the applications, right? There is some storage and 3 main stages, right? And that's somewhat native of those 3 stages. They basically realize the data ML paradigm I showed you before. 3 stages: data preparation, train and tune of the model, deploy and monitoring of the model itself as an application that can be consumed by other applications. Data preparation, we'll go into details of the 3 stages in a moment. In general, is from raw data to data that the model can consume. Train and tune is the moment when a raw model becomes a trained model on that data, and then deploy and monitor again. We put that live on an application. Right. What we did was jumping 1 level of abstraction lower at data flow diagram level 1 for the data ingest and prep phase. We have data scientists. They define and execute tasks such as cleaning up data, normalizing that data, transform that data, and label the data set. There is a data ingest step where data coming from all over the world would be stored somewhere, and this storage is managed by the administrators. Right, so we said, as usual in threat model, what can go wrong? A few things. A few threats were identified. At storage level, somebody, again, advanced threat actors, could inject data, poison the data, or compromise the quality in the ingestion storage, and they can do exactly the same on the pipeline storage. but they can also clean up critical data. And you would have a suboptimal trained model because you're missing the important data in your data set. Or again, they can tamper with the labels or with the labeling process itself. And when we identify threats, the next thing we do is always identify controls to remediate. Again, on the storage, there's a well-known set of controls you can implement, digitally signing data selectively, not all petabytes, implementing stronger RBAC on the storage operations, network segmentation, it still works, RBAC on the Kubernetes storage operations, secure manifest, and implement some sort of admission control and things like OPA to prevent unauthorized volume mounts. And on the tasks themselves, verify signatures of the data you load, sign the data you store, and implement strong RBAC on those tools. And for critical data, implement manual reviews as well. Next stage, train and tune. Data flow diagram level 1 for train and tune sees, again, data scientists and administrators. Data scientists, they define and execute these individual tasks, and spoiler alert, everything because runs on Kubeflow, aka Kubernetes, every single task is actually run as a container, same as Tecton, for example. Every task loads and stores data from the pipeline storage. Training, which is quite critical, also stores the checkpointing on the pipeline storage. That's the state where the trained model is. So you can resume training the model if you have a power outage of the cluster explodes. And then stores the training parameters on a dedicated server. Again, threat modeling, next step, what can go wrong? A few things here. So we could have a model degradation due to poison hyperparameters. Hyperparameters are quite critical before start training the model. We could have a pipeline compromise or bypass. Again, loading rogue containers, not part of the pipeline as it was defined. There could be model compromised via gradient tampering. It's quite sophisticated. Model degradation due to poison training data. Model compromised via parameter tampering. Again, obtaining a suboptimal training phase. And good old data injection or data poisoning on the storage itself. Threat modeling, next step. What do we do about it? We introduce controls. Again, leveraging Kubernetes and Kubeflow specific capabilities. Verify image signatures before admitting anything, sign images when building them, signing the output of each phase. For anything to do with the version control system, implement MFA, require signed commits, introduce two keys principle so that not a single data scientist can do a major change without a peer review, and on the storage, good old RBAC, secure manifest, and again, admission control and OPA. And again, access control also introduced for the parameters server to make sure that nobody can tamper with those parameters themselves. And over to you, good sir.
Thank you. Right, so we have gathered the data that we need to train our model. We have been through the training process, so we now have something built that we can start to ask questions from, plug into other pieces of software. We want to deploy this thing and make sure it runs as we expect. One point to note here is that serialization is a crucial step because this is where we take the trained model and package it into files that are loaded whenever it's run. This is almost like a form of compilation or packaging. Of course, these are the artifacts that are a useful point of injection for an attacker later on in the system. So, mapping the threats to deployment, of course, tampering or poisoning both the serialization step or the registry, which is the concrete compressed and OCI packaged version of that, means that any consumer later on suffer from either a form of supply chain attack or a tampering attack. We can mess with testing. Ultimately, there are so many points here that are very finely balanced, and it's so difficult for most AI systems to give you a rationalization and an answer for why they were weighted in a specific way or why they've made a specific decision, that any of these points of attack will persist into a model and are potentially very difficult to understand or detect later on. That rogue trained model potentially is indistinguishable from a less rogue version. Once we're serving the thing, it's just a TCP socket hitting some form of API, and if we can get in the middle of that, we can mutate whatever we like. I'm not talking about a layer 7 TCP, TLS breaking. I'm talking about being inside the application and just manipulating that data as it goes out. Of course, intrusion detection should discover this in our production systems, but it's another point where the trust model here, it just extends so far, as of course most software does. We see the front end model abuse via an unsecured HTTP endpoint. This, for example, is a good case for zero trust. As with everything, we trust nothing and verify as much as possible. And yes, the test results tampering sit in the same kind of place. So thinking about serialization, this is kind of similar to the salsa packaging step. Yes. There are a lot of analogous things in here to CI/CD. We can rely upon good practices from the rest of software development, let's say, and very much in the dev to DevOps style. So what are we looking at? Well, let's sign things. A signature means that the person in control of that key at the point in time that they used it liked the thing that they're creating signed metadata about. That's all it really means. It doesn't testify to the veracity of the thing. It doesn't say that it's definitely what the person expected it to be, but it does suggest that enough prerequisites have been met for a degree of trust to be put into it. Super abstract and just worth sort of playing through when we think about what and why are we signing things. So actually, in this case, you probably want to sign something that contained metadata describing the process that generated those things. And then back, you go through the provenance stages for each of those build steps. And this is this interstitial stage signing is akin to something like what Tecton does within Toto and chains. We rely on, again, these Kubernetes and container abstractions for signing an RBAC for the image registry. Again, the admission control for these things, we can just rely on this and treat it like it's a standard production deployment of containers. The front end, I mean, we use our best practices. OWASP have got a load of good things for a subset of those. And of course, coming back to signatures, signing our test results means that we actually trust them. Okay, that was the abstract version. The concrete version is Kubeflow, which warrants a threat model in itself because it is not unsubstantial. We need to scope it down or better do it at a higher level of abstraction. So running through things briefly, there is a lot of code in Kubeflow. It can do many things. It is a runtime for all seasons, almost. So we look at these training jobs. Each of these points, again, are ingress points for an attacker to start mutating and playing with the final output that we get from the other side of a terminal. Really, what we want for these things is a detailed decomposition of exactly how this is all working. These pipeline components are self-contained sets of code that perform one step in an ML workflow, so they're chained together. So, for example, pre-processing, training a model. And to create a component, you must build the component's implementation and define the component specification. Again, just a bunch of YAML, as we know and maybe love. Your component's implementation includes the component's executable code and the container images that the code runs in, interactive environments for writing and running code, documenting work, creating visualizations in a narrative format. Suffice to say, there is too much here for the rest of the talk, but good news. Tag Security are going to be doing a detailed assurance of Kubeflow in order to support its graduation through the CNCF. So if this stuff is interesting to you and you would like to understand either more about how these things are performed by some of the industry luminaries, some of the people in that group have been doing threat modeling for a very long time for very complex things, especially automotive-grade Linux. We've got one of the authors of one of the original supply chain security frameworks, PhDs in the field, etc. I'm none of those things, incidentally. We're going through and we're threat modeling this in the way that Francesco's decomposed this. Specifically for Kubeflow, we will generate a list of threats, a list of recommended controls, project recommendations for the development team and the security team to essentially take the Kubeflow project forward in as safe a way as possible. And the outcomes of those will feed into the graduation process as Kubeflow goes to aim to be a graduated process out of the CNCF. Some of the things that we will be talking about, the additional threats, I know there's a lot here and it's rather small. We will publish these slides to save your eyes. But suffice to say, there is a lot going on here. My favorite attack, as I've mentioned already, is this model inversion attack. It's not even something that comes from anything we've been talking about. It is once you get to the interface with the model as a consumer, and then you try and trick it to tell you either what it was trained with or what its prompts were. That's something that just requires access control on the front end. We know the solution, it's very simple. The question, of course, that we've posed today is, can you secure everything before it gets there? To which the answer is, with rigor. So, in conclusion, as always, threat models give us a quantifiable basis by which to deploy controls and countermeasures and ensure that we have a known state of the system that sits in a secure, steady state. The common threats that we have to all other systems still apply to AI/ML. There's no sort of magic, fancy quantum way of doing this. It is just bits and bytes and stuff running on melted rock. Some of these extended threats can be more complex, and this concept of configuration as supply chain, as part of the supply chain of a piece of software, is something that I know that there's a lot of work going on with coming out of Docker. I know Ilya, who's wandering around today, is talking about this as well. Essentially, if we're delivering something to a consumer, but then they configure it insecurely, what's the point? So anchoring the configuration for a piece of software, so that might be shipping network policies with your application, it might be shipping a seccomp profile or an AppArmor profile for a container. Those two things are inextricably intertwined. Supply chain right now doesn't even begin to bring that into the conversation. I think it really should. Collaborative approach is required to get this right, and please feel free to join us at any of the community events that we're doing. Huge thanks to Francesco. Any questions?
Thank you very much. Thank you. Thank you very much, Andy.